Hello, everyone, and welcome back to another session of this course. Today, we're going to break our narrative a little bit, and we're going to go back to a bit of cryptography. So let me share my screen, and I can then tell you what's going to happen today. Okay. So today is also going to be mostly a theoretical session in this course. And I'm going to cover something that I intentionally left out when I was teaching you about Diffie-Hellman-Merkle and also public key cryptography. And actually, I wanted you to first do homework 1 before you see this. So now is a good time to cover it. So just to remind you what we were doing here. So consider this scenario where Alice and Bob are communicating over an unsecured channel, and they wanted to have some shared key K such that both Alice and Bob can know this value K, but no adversary who's just seeing what's happening on the channel can somehow obtain it. And remember that we had this nice idea of key exchange, which was that, both of them choose some modulus P, and they also choose some constant primitive root G. And then each one of them chooses a secret number. So Alice chooses A and Bob chooses B. And then we had this very simple protocol. First of all, they exchange P and G, so everyone on the network knows about P and G. Then Alice computes G to the power of A and sends this over to Bob. And she can compute this because she knows A. Bob computes G to the power of B and sends this one over to Alice. And again, he can do this because he knows B. And then the idea was that, well, Bob has received G to the power of A from Alice, and he knows B. So he can just take G to the power of A and raise it to the power of B and get G to the power of AB. Similarly, what Alice could do was that she has received G to the power of B from Bob, and she knows the secret A. So she can just raise G to the power of B to the power of A and compute G to the power of AB. So as we saw before, what happens here is that G to the power of AB would be the shared secret. So both Alice and Bob could compute G to the power of AB, but we talked about what happens from the point of view of someone who's just seeing the communication over the network. So if you have Eve can just see P, G, G to the power of A and G to the power of B, but she can never see the actual values of A and B. So it's hard for her to compute G to the power of AB based on just this information here. Okay? So this is how we could do key exchange. Oh, a nice thing that is in the chat is that someone says Eve can pretend to be Alice and talk to Bob, and then pretend to be Bob and talk to Alice, and she can basically tamper with the key. Yes, so this is called a man-in-the-middle attack, and actually, yes, in this case, Diffie-Hellman is actually vulnerable to this kind of thing. So here, the model that we are assuming is that Eve cannot really tamper with the messages. So we just assume that any message that we have here between Alice and Bob is going to be delivered. And the only thing that Eve can do is that she can listen on the network and see the messages. So this is the model that we're working on here. Okay. Now, then after this, after talking about Diffie-Hellman-Merkle, we went on and talked about another kind of cryptography. So this was mostly for symmetric cryptography. If you remember, the idea was that we get a shared key And then we use that shared key for encryption from now on and also for decryption. And because only Alice and Bob have this shared key K, only they can encrypt and decrypt messages. But then we talked about this scenario of public key cryptography, where the idea was that Bob is not always online. Maybe if we said consider the case of an email server, so Bob can create some keys, some pair of keys in this case, and announce this to the network, and then he goes offline, and we want Alice to be able to send messages to Bob while Bob is offline. And we basically formalized this. We said that we need an encryption function and a decryption function, and we need to have a key pair, and we need to have these properties. So we have to be able to decrypt an encrypted message and get the original message. This was the definition of a valid crypto system. And then we said that an adversary who knows the encryption function and the decryption function and also knows the encrypted message should not be able to find the decrypted message. Okay. So, and then I went on to tell you about RSA, but now here I want to create a fork and talk about something else. So let's just create a fork here. And what I want to talk about is actually what we call the ElGamal crypto system. And this is very much based on Diffie-Hellman-Merkle key exchange. So just like Diffie-Hellman, I want to fix some prime number P, and I want to say that all of my calculations are modulo P. Okay. So write this. Is in Diffie-Hellman-Merkle. We fix, again, it should be usually a large prime number. So let's say we fix a large prime number P, and all calculations are modulo P. What we want to do is that we want to do public key cryptography. So we want to again have a situation where, let's say I have Bob on this side, and I have Alice on this side. And I want Bob to first create a key pair. So Bob creates a public key and a secret key and announces the public key to the world. So let's do it. Let me write it like this. So I write the secrets with red again. So Bob creates a secret key, and he also creates a public key. And I write the public things in blue, and he basically announces the public key. So let's say that our secret key is SK and our public key is PK. So Bob announces PK on the network. And then he goes offline. And so the idea is that now Bob is offline, but Alice wants to send a message to Bob. She should be able to just use this public key PK to somehow encrypt the message so that only Bob can later on decrypt it when he comes online. So what Alice has is the message, and this message is, of course, something that we want to keep a secret. And what she wants to do is that she wants to send to Bob the encryption of this message using the public key that Bob has already announced. Okay. So this picture is the same as in any other kind of public key cryptography. So the picture was the same, for example, in RSA. The difference is that here we don't want to do RSA. We don't want to have a multiplication of two prime numbers as our modulus. Instead, we just want our modulus to be a single large prime number P. And so the idea in ElGamal is that we can just look at what we did in here in Diffie-Hellman and try to turn this into an offline algorithm. So what can Bob do? Bob can just choose P and G and also this secret number B that only Bob knows. And then in order for Alice to send a message to Bob, Alice can just have a shared key K with Bob, right? But the problem is that if Bob is first announcing something and then going offline, then how can Alice get this shared key? And well, the answer, a very simple answer would be that Bob can just do all of his parts of computation. So he can just choose B, P, and G, and then he can compute G to the power of B. And he can announce all of these things. So all of the things that he announced here, P, G, and G to the power of P, and say that all of this is my public key. So now we are at a point where the public key is not just a single number, but it's like a bunch of numbers. So it has more information in it. And then when Bob goes offline, Alice, let's say, is online and wants to send a message to Bob. She can see the P and the G that Bob has chosen, and she can also see G to the power of B. So now she can generate A, and then she can generate K, and then she can send G to the power of A to Bob, and also use K to encrypt a message and send that message to Bob. And then only Bob would be able to decrypt it. So let's actually put all of this in context. So let's go back here and let's have another figure like that. So this is Bob, and this is Alice. So as we said before, since Bob is the one who's going to create the public key and the secret key, we let Bob choose our prime number P, which is going to be our modulus. And we are also going to let Bob choose our G, which was the base that we use for our exponentiation. So Bob creates a prime number P and some number G, which is between 0 and P minus 1. And so I don't want to draw it like this because he's not going to just give it to Alice, he's going to announce it on the network. So what I can say is that Bob announces P and G. So everyone on the network can see this, including Alice, of course, if she later wants to send a message to Bob. And then Bob is also going to have a number B, which, as we said before, is between 1 to P minus 1. Okay. And this is going to be Bob's secret key. So the secret key is just this number. And he's going to also announce G to the power of B to the network. And of course, all the calculations are modulo P. Okay. So he does these things and he goes offline. So maybe, again, you can think of this as creating an email account. So Bob creates his account, announces these things, says, hey, if you want to send a message to me, these are the parameters that you need. So basically now the secret key that Bob had, okay, let me write it on this side, sorry, the secret key is just B. But the public key that everyone has is all of these things. It's P, G, and G to the power of B modulo P. Okay, so the public key is now a tuple. So Bob announces the public key, he goes offline. Now, Alice is online. Alice wants to send a message to Bob and wants to make sure that only when Bob comes back online, he's the only one who can actually read this message. So Alice should somehow encrypt the message using this public key. Right, so Alice has this message M. And what we want to define is how to encrypt. So how would you encrypt using this public key some message M? Well, so as before, Alice can generate some random number A that only she knows, and then she can compute G to the power of A, right? Because G was part of the public key, so Alice knows G. And since she chose A herself, she can easily compute G to the power of A. And of course, she also needs P because all the calculations should be modulo P, and so she has to know the same P that Bob was using. So Alice sends a message to Bob, and the first part of this message is G to the power of A modulo P. Okay? This is the same thing that she would send to Bob in Diffie-Hellman. Now, what else can Alice compute? Well, Alice knows A, and she also knows G to the power of B, because Bob has put G to the power of B in the public key and has published it. So Alice can just take G to the power of A, and she can just take G to the power of B, which was already in the public key, and she can raise this to the power of A, right? So as before, what this would give Alice is G to the power of AB. So Alice can compute G to the power of AB, and remember that this was the shared key that Alice and Bob had in Diffie-Hellman. So she can just use this as the shared key K, and instead of sending the message, she can just take the message and add this K to it. And of course, again, all the calculations are modulo P. So she can just send these two things to Bob, okay? And this is how we define our encryption. We say that the encryption of a message M using this public key would basically also be a tuple, well, actually a pair of two numbers. The first number is just G to the power of A modulo P, okay? And the second number is M plus K, where K was this G to the power of AB, so I can just write it like this, M plus G to the power of AB, also modulo P. And of course, this encryption function is also assuming that Alice is generating some A for herself and keeping that secret. Okay? So this is how we do encryption. Now, this is a little bit unintuitive in the sense that we were used to this idea that our public key should just be one number, but now our public key is a tuple of three numbers. And we were also used to this idea that when we encrypt a message, we should get only one number as the encrypted message. But now what we are getting is a pair of numbers as an encrypted message. But this is fine, like the theory goes through. You can, as long as you can write these as sequence of bits, you can do it. Okay. So of course, they should also agree on the encoding and how they write, for example, a sequence of numbers, but that's fine. Now, why does this work? Because this is basically Diffie-Hellman, except that the timing has changed. Instead of Bob first announcing P and G, and then him announcing his part of the secret, which is G to the power of P, and then Alice announcing G to the power of A, and then both of them computing this shared key G to the power of AB, we are doing this in order. We are saying that first Bob announces P and G and his part, which is G to the power of B. So at this point, Bob has announced everything that he would announce in Diffie-Hellman. And so now, since Bob has done everything that he was doing in Diffie-Hellman, he can go offline. We don't need him anymore. And then Alice can come and fill in the missing parts. So Alice can come and say, okay, now I generate my number A, which I had in Diffie-Hellman as well. And I compute G to the power of AB, which is again what I would compute in Diffie-Hellman. And then the things that I had to send in Diffie-Hellman to Bob were, well, first of all, G to the power of A, so that Bob could also compute G to the power of AB. And then, of course, I would then use this shared key, which was G to the power of AB, as some type of one-time pad, so that we could do symmetric encryption. So I would do the same thing here. I would just take this key K as some type of one-time pad, and I will just add it to my message M. And of course, I'm taking it modulo P, so it is really a one-time pad. And then I would send this to Bob. So later on, when Bob becomes online, so if I want to give some order to this, so the order is like this. First, Bob is choosing this. Okay, let's do it like this. First, Bob announces PNG. Then he chooses this number B. Then he announces G to the power of B. Then we have Alice, who computes all these things. So especially chooses a number A. And then we have Alice send over this message. So this is the fifth part of the protocol in order. And now let's say Bob comes back online. So let's say this message was, for example, an email message that Alice sent to Bob. And now Bob is online. He can see this message. He wants to decrypt it. So actually, let me just call this one the encryption of M. And then now Bob wants to decrypt this whole thing. Okay. So he has G to the power of A, and he has M plus K. And he wants to decrypt this message. Okay, what can he do? Well, G to the power of B is public knowledge, right? And G to the power of A is also now given to Bob by Alice, and Bob knows B. So Bob just takes this G to the power of A and raises it to the power of B. Okay, so he takes G to the power of A, which was given to him by Alice, and raises this to the power of B, so he gets G to the power of AB. But remember, G to the power of AB was the shared key that we used in our one-time pad. So G to the power of AB would just be K. And now, given that Bob has this K, and he also has M plus K modulo P, he can just take the M plus K and subtract K from it, and then he will have the message. Okay, so this is the sixth step, basically, where the decryption, if I want to actually write it in a better way, I can write it the decryption of, let's call this part X, and let's call this part Y. So when Bob wants to do decryption, he has two numbers. He has X and Y. And what he does is that he first computes X to the power of B, which gives us G to the power of A to the power of B, which is the same as K, and then subtracts that from Y. So I just get Y minus X to the power of B. And as we wrote this before, so Y is M plus G to the power of AB, right? And X was G to the power of A, so X to the power of B would be G to the power of AB, so these two things cancel out, and so we just get the original message. Okay? So, as you see here, by just extending our ideas about what things can actually be put into our public key and like how long our message can be if we just allow these tuples here and these pairs here, then we get a public key crypto system based on Diffie-Hellman. And this is what's called ElGamal. Now, why is this secure? Okay, so let me just answer some questions here and then I will come back. So one question in the chat is, just to be clear, x to the power of g to the power of p modulo p is not the same as x to the power of b, which is why if can't decrypt Alex's message. Yes, that's true. So if you have another eavesdropper Eve here, again, she will see exactly the same things that she would see in the Diffie-Hellman case. So we have changed the order of the messages, but we have not changed what goes into those messages. So anyone who's eavesdropping here on this network would see P, G, G to the power of P, and G to the power of A, but they will not be able to see A and B themselves, right? And because A and B remain secrets, anyone who's just listening on the network cannot compute G to the power of AB. So this is, again, exactly like here. So from the point of view of Eve, what she sees is the same thing. It's just that the order has changed now. Okay. And another question is, why would one use this method over RSA? Well, one example of this is actually in your homework 1, where the extra credit problem in homework 1 could actually be solved using this method, but probably not using RSA. I'm sorry, just let me mute this. Okay. So it's not that one of them is necessarily better. There are just two different ways of doing public key cryptography. And the thing is that the assumptions that we have for their security are different. So why is this ElGamal's crypto system actually secure? Well, if you look at what ElGamal is doing, it's similar to Diffie-Hellman. So the idea here is that if I have G to the power of A, I should not be able to compute A itself, right? Because as an eavesdropper here, I'm seeing G to the power of A. Similarly, I'm seeing G to the power of B. And again, the idea is that if I just see G to the power of B, I shouldn't be able to compute B itself. So the security here is kind of based on the discrete logarithm problem, that it's hard to compute the discrete logarithm. It's actually a bit of a stronger assumption. So let's actually be very formal about this. So what is ElGamal's security assumption? Let's call it that. So the assumption that we have here is this. Basically, our assumption is that it's hard for an eavesdropper to break this system. So that means that given a large prime number P, and some G, which should be a primitive root modulo P, so the powers of G should create all the possible remainders. We want to say, given these things, and also given all this extra information that we have here. So we have G to the power of P and G to the power of A. It is hard to compute G to the power of AB. Okay, this is our assumption. So Eve is seeing P, she's seeing G, she's seeing G to the power of A and G to the power of P. But we want to assume that it's hard to compute g to the power of AB if she knows these things. And again, this is not exactly the discrete logarithm problem, because the discrete logarithm problem would just be to compute A based on g to the power of A. And if someone can solve the discrete logarithm problem, then they can solve this problem as well. But it's very similar to the discrete logarithm problem. And so it's also widely agreed that this is also a very hard problem, and there are no real algorithms that can solve this for large values of P. So again, the security here comes with an asterisk, but with a similar argument as in the case of RSA. And the argument is that we have this really hard problem in number theory, and no one knows a good algorithm for it, and a lot of people have tried. And the idea is that if someone can break our crypto system, then they have also been able to solve this really hard problem, which we think is unsolvable. Okay. But this is actually the main difference between ElGamal and RSA, because if you look at what we had in RSA, this was the RSA assumption. Okay, the RSA assumption was quite different, and it was actually based on factoring large integers. So our assumption in the RSA was that our modulus was this number n, which was a product of two prime numbers, p and q. And the idea was that if you don't know P and Q and you are just given N, it's hard to factorize N and get P and Q. So the security of RSA was mostly based on hardness of factorization. But here the security of ElGamal is not based on hardness of factorization, it's mostly based on hardness of discrete logarithms. So it's just that they have completely different security assumptions. Okay. So another question here in the chat is, shouldn't this be g to the power of a mod b and g to the power of b mod b? Mod p, yes, that's true. But okay, generally I'm just assuming that all calculations are mod p. So sometimes I write it when I want to really emphasize it. But even when I don't write it, the calculations are modulo p. So let's be very specific here. So we get g to the power of a modulo p, and also g to the power of b modulo p. Okay. So, but here's another thing. When we were doing RSA cryptography, one really nice observation that we had there was that we can basically use this for digital signatures, right? And the idea there was that, well, Bob has a private key or decryption key D and a public key or encryption key E, right? And the idea was that, well, everyone can encrypt messages and send these encrypted messages to Bob using this public key, but only Bob can read these messages and decrypt them using this private key. And when we were talking about digital signatures, we talked about this idea that we want only Bob to be able to sign something, but then when Bob does the signature, we want everyone else to be able to verify it. So the idea that we got there was that, okay, here's how we can get a digital signature. We can just think of it conceptually as saying that signing is the same thing as decryption, and verifying is the same thing as encryption, because signing is something that should only be doable by Bob, and decryption was like that. And verifying is something that everyone should be able to do, and encryption was also like that. So if you look at this idea here, it doesn't really depend on the exact crypto system that you're using. We are not really depending on RSA here. We are just depending on the properties of our decryption and encryption, on this idea that only Bob could do decryption. So we can say that signing is the same as decryption. And everyone could do encryption. So we say verifying is the same as encryption. So this same idea can also be applied to ElGamal's crypto system, right? So I can have signatures here as well. I can have a new definition of digital signatures, which is again very much like the same idea that we had before. So this is called ElGamal signature scheme. And the idea is again very much like before. So Bob creates a public key. And as we saw, the public key has several parts. So the public key has 3 parts, P, G, and G to the power of P. Okay, P, G, and G to the power of P. And again, all calculations are modulo P. So this is the public key that Bob will publish to everyone. And he will, of course, also have a secret key, which he keeps to himself, which is the number B. Right? And then we should be able to sign using the secret key, and we should be able to verify the signature using the public key. So if I have a message M, and if I want to sign this message M using my secret key B, the signature would be what? So we said that signing would be the same as decryption, right? But now I have a small problem here. And the problem that I have is that my decryption actually needed 2 things, right? So it needed G to the power of A modulo P, and it also needed M plus K. So when I was doing decryption, which I want to use as my signature, I actually needed some extra information here. Okay. So now the things that I can sign should also have the same format. So here's how I would formulate this. I can say that Alice wants Bob to sign M, and Alice creates this A and sends this thing to Bob, okay? So when I want to sign, now again, another way of looking at it is like this. So the decryption took 2 numbers and did the decryption, right? So now my signature is also not going to be a signature on just 1 number. It's going to be a signature on a pair of numbers. So that's just because my decryption function looked like that. So my signatures are going to be signatures on pairs of numbers now. Okay? So when I want to sign as Bob, I will sign using this secret key B. But what is it that I'll sign? I can sign a pair of numbers. So I can sign the pair XY, for example. Okay? And the way that I sign this is exactly the same as my decryption function. So it's y minus x to the power of b. So this is how Bob would sign this. So if you give Bob 2 numbers, x and y, a pair, and you say sign this pair, Bob would just give you y minus x to the power of b, and this would be his signature on this pair. And now, after Bob has signed, if you want to verify it, and again, the verification is something that everyone should be able to do, and the signature is something that only Bob should be able to do. So the signature is the same as decryption as before. But the verification is going to use the public key that we had here. So in order to verify, you will need the public key, which has all 3 parts. And what do you need to verify the signature? Well, you of course need the signature itself. And what you want to do is that you want to just do encryption now. Okay? So you get some signature S. Okay. And actually, let's think of this verification as also having X and Y. So we can do that, or let's just have S. We can do both types of verification. So I've talked about this before, and some of you asked me about it in homework 1. So when we have a signature scheme, we can define our verify function in 2 completely different ways. One way of defining it is that the verify function gets the signature and just tells us if the signature is valid or not. So it gets the signature and also the message and just gives us 1 bit of information. Is this signature valid or is it invalid? Another way of looking at the verify function is that it gets a signature and gives us the original message. But these 2 definitions are equivalent. So basically, the difference is whether the signature contains the original message somehow encoded in it or not. And you can always use any of the 2 definitions that you want. So in this case, I can just use the Boolean definition. So I can say, suppose that someone gives me this pair XY that was signed and also gives me a signature on them. So let's say I've been given S, X, and Y, and I want to verify. I want to see if S is really a signature on XY, and if it's a signature that was created by Bob. And in order to do this verification, I can use my public key, right? And again, as we said before, this is just going to be the same as encryption, right? So what does this mean? This means that if I want to do this encryption, I have to now be able to give S and get back X and Y, right? So now, as you see, in a sense, the creation of the signature and the verification of the signature can also become interactive, right? So when we were working with RSAs, with RSA signatures, the idea was that Bob could just sign something and everyone could verify the signature. But now we can do it so that Bob can sign something and only Alice can verify it. Right? And this is what really makes these kinds of signatures more useful. Because you see, as before, what Alice can do is that suppose I have a message M, and I want to get this message M signed by Bob. So suppose that, for example, Alice is a bank, and the message M is that I want to transfer this much money from this account to that account. And let's say that Bob owns that account. So Alice needs a signature from Bob that this is really, this command is really coming from Bob, and Alice would then do it, right? So now what Alice can do is that she can do this signature in an interactive way, in a sense, right? So she can first send this thing to Bob. So she sends this message to Bob, and if then Bob can decrypt it and send it back, that's the same as Bob having signed this. Okay? So let's say that Alice wants Bob to agree with M. Then Alice just chooses a number A and sends this message to Bob. And now Alice knows that only Bob can decrypt this message. So if Alice receives M back on the network, she knows that Bob actually did this decryption. So we can think of this decryption again as a signature. We can think that this was Bob's signature. And this is the idea that we will have here, okay? So let me erase this because it became too complicated. But instead, I would just call this ElGamal's, let's call it interactive signature scheme. Okay, so Alice wants Bob to sign some message M, which means that she just wants to get a confirmation from Bob that Bob agrees with M. Okay, so what does she do? She sends this message to Bob, right? And this message is again based on just a secret that only Alice knows. So she sends G to the power of A and also M plus G to the power of AB to Bob. Remember that this is again the same as our encryption, right? So the intuition is just like RSA signatures. The intuition is that the person who wants to verify the signature, in this case Alice, can do encryption. But the person who wants to provide the signature, in this case Bob, is the one who is the only person who can do decryption. So Bob decrypts this message and sends M back to Alice. Okay. Now, again, this decryption is the same as signing. So instead of saying decrypts this message, I can just say signs this message. And signing is basically computing M from this pair. Okay. Now, why can we really think of this as a signature? Because if Bob does not agree, if, for example, let's say M is a message that says, I want to pay $100 to Carol from the account. And let's say that Alice is the bank and Bob is the customer. So Alice can just send this message to Bob. And if Bob sends M back, then Alice knows that, okay, Bob did decrypt this message and he also agreed with it, so he sent it back to me. But if Bob does not send this M back, then Alice just knows that, okay, so Bob didn't agree with it. And no one else can compute M, because computing M is basically decrypting this encrypted message. So let's go back here. So I first encrypted M, this was the encryption, and then computing back M is this decryption, right? So as Alice, if I receive this value of M on the network, I know that it was definitely created by Bob. And I know that no one else is masquerading as Bob and pretending to be signing on behalf of Bob. But here's another thing. This is, in a sense, a private signature. Why? Because, again, let's see who can verify this signature. The person who can do the encryption can verify the signature. So Alice can verify the signature, right? But our encryption also had a secret in there. It had this number A in there. So that means that if I have an eavesdropper, if I have Eve on this network, Eve cannot be convinced that Bob has actually signed M. So this signature is only convincing to Alice. So as you see, we have the exact same idea as the one that we had for signatures in RSA. And the idea was that, let's say, encryption is the same as verification of signatures and decryption is the same as actually signing. And this idea led us to something that is probably kind of more useful, because it's now a kind of signature that also has a recipient that can only be used for proving things to Alice. We could, of course, do the same thing with RSA as well. We could just combine RSA signatures with RSA encryption. So we could have a situation where Bob signs a message using his RSA identity, and then encrypts that message using Alice's identity and sends the encrypted signature to Alice. We could do that there, but here we get it in a much more natural way. Okay, so generally there is nothing that we can really do with ElGamal that we cannot do with RSA and vice versa, but they kind of have a nice and different flavor like this. So the signature scheme here is kind of interactive by default. Okay. Yeah, so this is all for this session, and you guys can leave now. Thanks for attending. I'm going to answer the questions in the chat. Okay. So let's look at the questions in the chat. One question is, so in this scheme, Bob can only sign something that Alice agrees with. Well, here's the thing. Bob can sign anything for anyone, right? So instead of just having Alice, we can have several different people, and each one of them can ask Bob to sign something, and they can use different values of A, and Bob can sign it back for them, and only those people will be convinced by the signature. So anyway, it's kind of like public key cryptography, but it's like public key signatures. And so this idea that Bob can only sign something that Alice agrees with, I wouldn't say that's exactly the case, because again, if you have, for example, Carol here, and then Carol asks Bob for a signature on something, then Bob can also provide that kind of signature, and it would be convincing for Carol that Bob has actually done that signature. And generally, another nice case is that sometimes this A is not just some private knowledge that only Alice has. If A is also something that is public, so if A is something that everyone knows, then everyone can verify the signature, right? So the whole reason that here we had this kind of interactive signature scheme that only Alice could verify was because verification depended on A. If we make A public, then everyone can verify. And this would then again be kind of similar to the properties that we had in RSA signatures. Again, this is why I said there is nothing that you can do with RSA and not with this system, or vice versa, conceptually. Okay, so another question is, how can the bank predict that Bob wants to send money? So content of M that the bank wants Bob to confirm. Well, I mean, we're just assuming that here. The use case was, again, to have someone sign something and to have it be convincing for you that it was really them who signed it. So in the bank example, suppose that you have, for example, a bill from an energy company. Let's say you want to pay your gas bill or your electricity bill, and they send the bill directly to the bank, and then the bank can send some message to you and say, hey, do you agree to actually pay this bill? And then you can just sign it, and your signature would say, yes, I agree, and then they can deduct it from your account. So another question here is that, so in this scheme, we first verify, then sign the message. In a sense, yes, because we are first doing the encryption and then doing the decryption. But actually, if you think about it, the verification is really done after the signature in the sense that, well, so let's say Alice wants Bob to sign this M. She first sends this message to Bob, right? And then Bob should send M back to Alice. And only if Bob sends M back, Alice would be convinced that Bob has signed it, right? So the verification is kind of like comparing the number that Bob sends back to you, if he sends anything, to M, right? So It's not exactly that the verification is being done before the signature. The verification now has two phases. One is this phase which is done before the signature, and one is the comparison that is done after the signature. Okay. So another question here is that, is it a requirement for symmetric encryption that both Alice and Bob need to be online at the same time to do the communication? I remember you mentioned an advantage of asymmetric cryptography is that Bob and Alice can be offline, as you said just now. But why does symmetric encryption require that? So this is not a requirement of symmetric encryption. The requirement that we needed Bob and Alice to be online at kind of the same time was because of this key exchange, right? So when you want to do this key exchange, this is an interactive protocol, because first Bob sends something to Alice, then Alice sends something to Bob, then both of them compute a shared key, and then they use that shared key to communicate. So in a sense, what Bob sends over the network is dependent on what Alice sends over the network, and vice versa. So we cannot have a situation where Bob just goes offline, goes home, and Alice sends a lot of messages to Bob. But here, as we saw, because we just changed the ordering, and this was a very simple change, now Bob can first send all the messages, and then he can go offline, he can go home after announcing this public key. And then Alice can send as many messages as she likes to Bob. And then Bob can come online later on and read all these messages. Okay. So another question here is that, so the message must be from the other one first. So Bob cannot sign a message from himself or on his own. Yes, actually, this is true in the way that I explained it here. But this was assuming that this number A is also a secret, right? So if Bob wants to sign a message and wants it to be provable to everyone that he signed that message and not just to Alice, then he can also just use a public A. Okay? So if Bob announces P, G, and let's say he announces G to the power of P, and he also announces A publicly, so also puts A as part of the public key, then everyone would be able to see A. And then when he wants to sign a message M and prove to everyone that he's the one who's signing M, he can just do the same thing. So he can do the encryption here on his own, and then the decryption and so on. And this basically proves it. But again, this is not great, right? So yeah, usually we don't want this A to just be chosen by Bob, but anyway, anyone who knows A can verify the signature. So if A is somehow known to all the people that you want to be able to verify the signature, or if A is public, then this would be easy, but generally we don't want Bob to choose A normally. So another question here is, what if Alice herself is an attacker and she knows M? She can just impersonate Bob to send M back to herself. Yes, that's true, but again, the role here was, like the protocol here was focused on convincing Alice that Bob is signing M. So this is actually another reason why if you just do this interaction, only Alice will be convinced that Bob signed it, and no one else will be convinced, right? Because everyone else will just see this signature and it doesn't mean anything to them. And yeah, actually the thing that I said about Bob announcing A himself, that's wrong, because then it becomes nonsensical here. The encryption doesn't make sense. But yeah, again, if Bob wants to prove this to several different people, then the requirement there would be that these different people should all share this value A. And then when Bob does this decryption, it would be proven to all of them that Bob did the signature. Okay, any other questions? Okay, and another question is, how can the extra credit question use this ElGamal? Well, the way you use ElGamal is that actually you can just think of this signature scheme. So what is this signature scheme proving? We are saying that it's proving that Bob agreed with M, because we are saying that if Bob did not agree with M, he would just not send M back to Alice. Right? So if Alice receives M back, she knows that, okay, it was Bob who decrypted it and sent it back. But what does Alice exactly know? What Alice knows exactly is that whoever could get this encrypted message and decrypt it back to M must have known must have known the secret key. And what was the secret key? The secret key was this number B, right? But Alice knew G to the power of B. So basically what Bob is doing here is not only that he's proving that I accept M because he's sending M back, but he's also proving that I know B, right? And that's basically how we know that it's Bob. Like, we assume that someone is Bob if he knows this secret key B. So basically what's happening here is that we have some public knowledge, which is G to the power of B, and Bob is proving to us that he knows the exponent B. And this is exactly what we needed in the extra credit question. So this is how this would solve the extra credit question. And actually, there is another way to solve that extra credit question, and it's called zero knowledge proofs. So if you just search for zero knowledge proofs on Wikipedia, you will find another way of solving that. And I think the Wikipedia article solves that problem exactly. Okay. Great. So see you all in the next session. And this was really, I promise this was the last cryptography lesson, and we will go back to smart contracts and vulnerabilities in smart contracts from the next session. So have a great day and bye.